Well, I'm going to let him explain. Josh, take it away.
Hi, I'm going to talk about how to use Golly, which is the most advanced cellular automata research tool. Second, maybe to Wolfram, but language, and how to use Python with it, since it supports two scripting engines, Lua and Python, and this isn't going to go into Lua for obvious reasons. A disclaimer, everything in the presentation is not related to my job. Somebody actually got confused about this. Also, all this, most of the research I did was in college. More specifically, I had a professor I was working with who was the former president of Cybernetics Association of America, and we were doing some studies using game of life like cellular automata, and I mistyped a number into my system, and I accidentally found a similar cellular automata that has certain properties, rotational symmetry. Also, preparing the presentation, I found the minimal thing to input to get the rotational symmetry. So now I actually understand this rotational symmetry much better. Who am I? I'm a longtime member of ChiPy. Been here for at least 10 years. Currently, I'm working in the finance sector for bank. I've given talks at DEF CON, Pi Ohio, React Chicago, ThoughtCon's another InfoSec conference. Yet again, none of this talk is about my employer activities. For cellular automata, I'm only going to go over the theory, but not all of the things like glider guns, gliders, or any of those things. I'm going to just go over mainly how the rules work, because the things that you'll study in Golly or in other similar systems would be just either start changing the rules. There's been a lot of research done just to game of life that actually is the most impressive one, which is the Turing completeness of the game of life. So the game of life is two-dimensional, two-state cell automata discovered by John Conway in the 70s. Von Neumann and another researcher actually discovered cellular automata, but the game of life popularized it. There could have been a few reasons for that, but it basically, for it, we have this B2S23, which is a notation of the cellular automata to either be create one or born or survive, meaning for each cell, you have the adjacent cells, and if you have two, you get one is created on if you have at least two adjacent, and the adjacent ones are one distance away of all the cellular automata. And for here, if you're on, then you turn on. I think I got these first. Otherwise, you don't survive or you turn yourself off. So Golly uses this notation. There is other notation by Wolfram who uses like all 256. It's called M-cell notation. Like B that has a set of numerals, and that's the counter. So the counter of the adjacent things of the cell to turn on, and you have to go through it's a numerical list of, and S are the numerals that you stay alive. So you basically count around your perimeter. So this is a very zoomed out version of the cellular automata that shows turn completeness. And you can see that if you were running it, you'd see that there would be glider guns hitting other glider guns and changing state of the system. So a summarization of lifelike cellular automata would be you eliminate the rule, but you still have all of the same examples, such as you still have an infinite grid. The grid is still, not still a grid or a lattice still. You still have the living or dead property, and you still have a pure function from the first step to the next step. An example of pure functions would be floor in Python, or examples of things that are like is anything that would have to do with mutation when you call it again. I believe a good example would be yield in Python. And below is B2, S23 is the rule for a game of life. And here's another explanation. So in this 3-cell cellular automata, in the game of life, it would just iterate 3 and then one direction, and then 3 in the other. It would just keep on pulsing. But here is, you can see that on the right are the examples of the pulse that would occur. And this is a few steps into the animation, which I call flake. Originally, I had a door or a cell that had a bunch of the whole square on the outsides as a square. But now I realize that what was happening was these 3 sets were just hitting each other and refracting over them. So while it would be sort of like a rotational symmetry. I didn't see that this is like the actual result. So Snow Life has a different rule where you survive on different numerals on the adjacent items. Because of that, it survives on specific numbers. It's an explosive example, and this is from the blinker. So a blinker is a pad. So in the game of life, there is a set of examples or blinkers. Gliders go like from left to right, and those basically reproduce themselves at every time interval, but they'll just be affine or just shifted over one to another, but they'll pulse. So this is it, where I found it by accident. Had a different rule, and it had these interesting properties. There were other derivatives found in my professor, so he called them Life 7, but I'm only presenting it on this one because so I don't have to ask for permission. So let's get onto the Python scripting. So there's a gotcha here, which I wanted to mention. If you install Golly and you see errors in Python framework, Golly is it only uses scripting really as intended if it's already in your path. So on Mac OS, if you get an error about Python framework, you have to, this sort of glitchy on how to do it, because I think you'd have to install Python using Homebrew, because when Golly's sort of old school, it's still on SourceForge. It's mainly using Python literally as a scripting, which means it's probably using C types. But because on Mac OS they just removed Python framework or the default Python install, it tries to look for Python framework and it'll fail because they don't even embed. Because, well, either they didn't want they don't want Python either in the default install. They expect it somewhere, either for license reasons or they just don't know that they should be doing it. There's probably a way to fix that. I think there's an open ticket about that. So this is a simple program that will initialize a blinker like here. Like you can do a blinker and you can see it's the life one. This is just without using a script. These MCs are just, MCs are just initialized values on the grid. So we can just, I can hit the space bar to just initialize it to go 1, and or you can hit the, it's not much that interesting. For obvious reasons. But now you can see flake MC, but you can also see that the rule changed. So see blinker MC life, snow life, and then you can hit. It's more interesting if you zoom out. You can do, fit pattern, Apple F is very useful. And it's a pure function because I can just go, you can go backwards and just go back to the beginning. And like, as you can see, the Python files are actually in directory Golly 4.2 Mac. And this is actually still in the applications directory. So it's applications, it's in a folder, and then this app. And it'll only look for the Python scripts there. I mean, it's not going to, so it's really old school implementation. So this is a glider in the rule I found in the rule that I found, but that somebody else made. You can see the gliding. Then let's do F. You can see that it's moving. That's the wholeness of a glider itself. Question? Yeah, I think you can ask is there an example of von Neumann's universal constructor? Yeah, there is it's not just lifelike Cellular Automata and Golly, there's a lot of other ones. So do you mean the rule set? Yeah, I'm sure there's an implementation in this. I don't know if it's here. But I'm sure you can find an MC file or the rule. You might have to find a rule or the MC file to do that. But I'm pretty sure if you go on the Life Wiki, Game of Life Wiki, which I'll have here, and yeah. So this is the code that I made because even though they found the glider, they only posted it on the Life Wiki, but they did not. But it was windowed in a browser. And the easiest way to illustrate this is make a simple Python script. So there's a rule here. You can see that first I import star because that's the best way to do things in Python. I don't, like, all of their examples do fromglife import star. And then I do my rule, and the rule is global. So even though we're talking about this is still not a pure function. And then you have this really arcane pattern, and then the pattern is just the serialization of the glider itself, which I can cut, was figured that you can cut and paste and do that.
So is that pattern the initial state? Is that the
Pattern, yeah, is the initial state of the glider that I showed you.
and then the rules are defined?
So I think this be better. So we have the import, and rule binds some kind of context variable. I think from my understanding, rule by default would use the game of life rules, but once you override it by running the rule method or rule global method, it will replace it. It will replace the current rule, whatever it is, with snow life, with my rule. This also will initially only understand that it's a lifelike automaton, cellular automaton. There's a lot more to Golly itself. It supports 10 or more ways to program, like with colors and so forth. So it's it's a very complex tool, and it's basically all the scripting is some kind of C types FFI to C++.
Is that readable to you? Are you able to discern things from the three?
I don't know. It's not really readable to me, but I believe it's a run length encoding, which means that there's actually a readable pattern. That's a good question. There is a readable pattern if we go in the docs. I'll open the docs for that.
That's right. I just wanted so it's not. I shouldn't be expected to read it.
Yeah, I think it's compressed on purpose. Like this is me.
Find that in the editor and then render it out.
Well, I think you can either define it to the editor or have it output the MC file, open the MC file up, or just export it. There has to be a way to export it. I imported this though from the Game of Life wiki. So the Game of Life wiki, it's a subgroup of people that are studying all cellular automata. They literally have like in Hypothesis before, you could just fuzz test randomly. They decided, what if we just fuzz test all 2D cellular automata, which they're trying to do. They literally are trying to do that. You can look on their website. So here you can see the specification of a rule. You can see parts of the user interface, and also like the zoom out one. Here the weird parts are showing. Scripts have to be inside the Golly directory to be read. It's sort of like Visual Code, except you can't specify your directory, or Jupyter, regular Jupyter, where you're sort of, before Jupyter Lab, you were sort of fixed onto the invocation of the directory itself. There's a guide and a help guide online. I talked about the macOS information, and the Golly itself was C++. So any questions?
I noticed that the site you posted is on SourceForge. What version of Python does this run under?
I'm running, so if you recall what I said about the framework, the answer for you is I'm believe I have the Python framework pointed to at least Python 3.9. So it runs on a modern version of Python. It's that only gotcha when it can't find the Python framework, but that's just because macOS, macOS thankfully removed Python from the default install so that we can install it. I mean, that wasn't really a joke. We have real, when you have Python your OS and when you have Python in the default install of an OS and you want to develop on Python, there's going to be some weird workarounds, and it might not be just virtual environments.
The rule, where does that come from? Is that a predefined set of rules? You're actually in a syntax for that, the domain and the yeah. So is that hard coded? Is those are the rules that there's a bunch of known rules that you define, or does that specify the initial board state, or what is the?
This is the board state. This is the transition function. So then we go to a hypothesis on Haskell sort of, if you know what a monad and IO isn't a pure function, which is the funny part, and a lot of Haskell is a pure function. Like I said, floor is pure. If you go back to so it's a generalization of the rules. They call it Murex celebration. I don't know why. So if we take the game of life's rules, which were originally made by Conway, and then relax them into the born and survive rules, I think that's 8 factorial on B, S as 8 factorial. So there's and then you multiply them, but you might have to divide by something. So there's not a preset a fine of rules. There's a large set of rules. Think of it and it's not an ordered, so it's not a partially ordered set. It's a large, very large finite set. So that's why when I said why they're trying every possibility, there's no, and Wolfram, a long time ago, I actually got a new kind of science, and I read parts of it and didn't like how it was written. But Wolfram is famous of studying cellular automata, and there was a large amount of cellular automata, not just game of life, but there's probably, this one is interesting. If I showed you an uninteresting one, this would be a really short presentation. But I've talked to other people, and there's a large amount of the cellular automata that are boring, but there's probably a small sliver of cellular automata that are interesting, yeah. Mine is sort of interesting because it can, I think it's pretty random, but it has rotational symmetry, which I've never seen in one, but I never seriously researched it, but I've never seen that one like that. With the rotational symmetry, we could almost think that it's subsets for one-dimensional cellular automata interacting with each other. Take a sliver here that translates into a 1D one, but maybe it's actually, but the edge is connected like a torus. So if you think of it like a donut, but think of it like a donut, a circular, not torus, it's like a circular cone. Torus is donuts and asteroids, because it has a symmetry, we want to be a circular cone.
What draws you to this? What is the piece that is fascinating to you?
Oh, that it's actually something interesting I found in mathematics.
What is the interesting part? What is the,
Well, that is an interesting cellular automata. A lot of mathematical proofs are found Like code as data is what codes are actually proofs, or programs are actually proofs. It's a famous theorem where like a theorem is a proof of like some kind of invariant, especially when you get correct. People that you've had scale or that's a whole other discussion about that thing. But the reason why it interests me is I had a large math background. I wanted to really get something like published, but I probably should publish this more. But it's like finding a method. It's like finding a dinosaur's bones. A lot of math is like theorem based, but this is more like discovery based. So it's like finding a dinosaur that nobody else found. Yeah, you either survive or you create. You have created, yeah. Yeah, so the statement was, I think, so von Neumann's universal constructor was to create a machine that would implement itself. Yeah, that is something. I think the proof that it's a. So if we go back, actually no, this is actually a proof of what you want. There was a Hacker News post, but it's a pretty obvious post is like, can you create an object, like a model of computation that can reproduce yourself? And once you have a Turing machine, you basically just use this, you transpile the code into this. And then your basic, but like you'd want to have something much, you wouldn't do like Golly itself. You just create a cellular automata that is lifelike, and then you re-implement that. You could, if you wanted to create different programs, and you just load it in and you change the inputs. But yeah, you can do it. I mean, this Turing machine proves that. There's many other ways to do it, but yeah. Yeah, I may have had more than one because it.
Yeah, that's what. So I just want to understand. So if we see B3 at 1237, we're saying if we have 3 neighbors next to us, we get more.
Yeah.
And then if we have 1 neighbor, 2 neighbors, 3 neighbors, or 7 neighbors, we survive.
Yeah.
All right. Good question. That's all.
Yeah, I wasn't clear about that.
Can you repeat exactly?
Yeah, so the question was, what does B3S1237? B3 means you are born if you have at least 3 adjacent members distance 1 cell across from you. There's a very specific, I don't know how much theory I wanted to put into that. And then you survive if you have at least 1 adjacent, 1 that's adjacent in that neighborhood, 2 adjacent in that neighborhood, 3 and 7. So it's B3 is basically born on the set of numerals, or natural numbers of 0 to 7 or 8, and survive is a set of numerals. So survive on 1, 2, 3, 7. Sure.
You mentioned neighborhood then. Does this notation support situations where you have cells that are farther than 1 away?
You have to, that's another generalization. Golly does support it. The question was, is there a generalization, does this support a generalization that supports a distance of 2 instead of 1? The answer is, I believe there's a modification of Golly that supports that. I believe Golly supports that. If not, I mean, you could either code it in Python, but, well, no, coding in Python would be a bad idea, but yeah, you have to look at, you'd have to look at the rule sets, but I'm pretty sure there are, or Yeah, I wanted it to be a little bit easy. We can go harder. There's one that I think density. There was one that I thought, yeah, this is the one. Because somebody asked about a torus. Also, Emacs is the only editor. Okay, so at least this one, they import Golly is G. I think, I didn't cover that. So this, I think, is controlling the UI. This is, so if we recall the other pictures where there would be just a matrix, this, you can see, use the current selection to create a toroidal universe. So so what this is going to do, we could run it. Oh, no, maybe it does not. Oh, I have to make a selection. So we first have to make a selection, so we use the selection tool. Then we run the script, make torus. Then now we can make the toroidal universe by hitting the green button. And now it looks like we have a fixed point. So it's basically asteroid rules. Top is loop to bottom, left is loop to right.
Yeah, I can see that. Wolfram, like, he was trying to use this to determine if there's a small set of rules that could determine, like, the execution of the universe, basically.
Yeah, Wolfram did the 1D ones and then found Rule 30. 2D, I mean, what in the New Kind of Science, I've sort of read it, but he's heavily criticized in that book for not giving credit to the people. So I'm going to do right now, a lot of this is from Wikipedia to do the presentation, the Golly documentation, which is really good. But when I was reading this book, the concept was a new kind of science to suppose that cellular automata and other like complex emergent functions would be created by like simple rules, such as cellular automata. He's famous doing his own notation of Turing machines, which also look like cellular automata, 1D ones. I'm not sure why he didn't do more research in 2D, other than it's very hard to do. And ever since his book has been come out, there really hasn't been much that has been done about the new kind of science, because I actually did read parts of it. I asked my local library to get a copy because it's $100, because it's not because he overcharged. If you actually look in the book, he has a very high resolution things, especially when you're dealing with like cellular automata. You need high resolution books, but then around 10 years ago, he just made a PDF for free, and then he has some kind of workshop that he uses to re-educate people about it.
Are there any implementations that simulate more than two dimensions?
So the question was, are there three-dimensional cellular automata? I don't know of one. Golly does 2D only. If you're going to 3D or even non-cells type, you're not going to find it in Golly, but you'll but finding them online would be probable. Although you could see it as an exercise to do instead of additive code, you just write a 3D cell automata in Python and then output it. And then you can just remove the 3D part and we'll have something to talk about in 2D. So. And I suggest using NumPy, so hopefully get GP. I actually had an idea maybe to do GPU acceleration for this, but on the other hand, I don't know if it would help because of memory limitations. That may be true, but you can change the algorithm.
All right, any other questions?
Well, you consider collaborating with Paul and seeing what happens when you put an automated buzzer on this?
Yeah, I did think about it, that, like, the search, even though it sounds like a joke, there is no concept. And Wolfram, I think, also mentioned about this. There is no way to deduce if one is interesting or not, or there's no, you have to, people are just brute-forcing it. How do you have there's no prior intuition about whether a cellular automata will be interesting unless you test it. So, and you have to define the concept of testing. So what you'd want to do is have a script that there was so what you'd want to do, the only way I could think of would be to randomly initialize the set of cell automata and then compute the entropy of it of a few steps. But even that in hypothesis, you'd have a long-running hypothesis system, and I don't. And that might be really similar to, so when we go to the Game of Life wiki, so there's two wikis. We're not talking about, don't look this one, we want to go this one. Then when you go here, there's a section of here. There's a section here where they're actually, catalog. And you can see what they're doing. They're brute forcing things.
Brief closing announcements.